So suppose V is a vector space. We can define subspaces of V in exactly the same way that we define subspaces of Rn. So a subspace of V is a subset that satisfies the following three properties. The first property is that 0 is in W, and remember that this refers to the zero vector of V. And if the vector space operations are weird, then 0 might not look like 0. The second condition is that if you have two vectors that are in W and add them together, you get another vector that's in W. And then the third condition is that if you have a vector in W and you multiply by any scalar, then you'll get something else that's in W. And note that conditions 2 and 3 involve addition and scalar multiplication, and those are the operations from the vector space structure of V that you're going to use. So again, if those are weird operations, then you would use the weird operations in this definition. So this is literally just taking the definition we learned earlier and rephrasing it in terms of general vector spaces. But there's a key fact about subspaces that we're able to state now that we weren't able to state before. And that's that if you have a subspace of V, then that subspace is itself a vector space. And what I mean by that is that you can use the same addition and scalar multiplication rules that you have for V. And with those addition and scalar multiplication rules, W will satisfy the axioms of a vector space. Let's go through those axioms and try to understand why this happens. So the first axiom is commutativity, that U plus V is equal to V plus U. But here's the thing, in this situation, V is already assumed to be a vector space. So we already know that the addition in V is commutative. And then because we're using that same addition for W, we automatically know that the addition in W is commutative. Now here's the cool part. The exact same logic that we just used works for most of the axioms. It works for associativity, the distributivity laws, the scalar associativity law, the one axiom. All of those axioms are true in W because they're true in V and we're using the same addition and scalar multiplication. The only vector space axioms that don't automatically hold like that are the existence of 0 and the existence of minuses. But you'll notice that the first axiom of a subspace is that the 0 vector is in W. So W does have 0. Now the existence of minuses is a little more tricky because it doesn't directly come from an axiom that's out there, but there's a fact about vector spaces which you can prove, which says that if you take any vector in a vector space and scalar multiply it by -1, then you get the minus of that vector. So subspace axiom 3 says you can take any vector in W, multiply it by any scalar, and you'll get something else in W. So in particular, you could multiply by -1, and you would get something else in W. But then we know that that thing that you would get when you multiply by -1 is minus V. So minuses exist in W. All right, so that completes the verification. If W is a subspace of V, then W is itself a vector space. What's great about this is that it gives us a nice way to prove that certain things are vector spaces. Rather than having to check all 8 axioms every time, if we can recognize that something is a subspace of some vector space that we already know about, then we can automatically conclude that it's a vector space. So this means that ultimately we're only checking the 3 axioms of a subspace instead of checking the 8 axioms of a vector space. That's nice. All right, so let's put this into practice. Recall that if you have a set S, you can form a vector space f of SR, which is the space of functions on S. So that means that the inputs of the functions are elements of S, and the outputs are real numbers. Now this is a pretty general construction because S can be anything, but for a lot of purposes it could even be too general. So here's what I mean by that. Suppose we're just talking about functions on R, where S is equal to R. So this is just the space of functions, the f of x, where these functions are supposed to be defined for all x. But it really does include every f of x, even really weird ones. So what happens in practice is that depending on what you're trying to do with your functions, you might impose additional restrictions. So like maybe you only want functions that are continuous. And so you can define a subset of f of RR, which is the subset of continuous functions, and this is a subspace. Let's go through the axioms and understand why. So for the first axiom, we just need to observe that the function f of x equals 0 is continuous. And just to clarify, this is the function which when you graph it, its graph is just the x-axis. So it's the function that's 0 for all x. That's the thing that plays the role of the 0 vector in f of RR. And because that function is continuous, it's also in C of RR. For the second axiom, we observe that if you take two continuous functions, f and g, and add them together, the result is continuous. Now, a rigorous proof of that fact would require some analysis, which we're not going to do in this class. So you can take it for granted if you want, but hopefully you're willing to believe that it's true. And then for the third axiom, we observe that if you have a continuous function f, and you multiply it by a constant k, then that's also going to be continuous. And again, rigorously proving that would require some analysis, but I think you'd probably be willing to believe it, and we can take it for granted in this class. And so the upshot of all this is that continuous functions form a vector space. We can talk about the vector space of continuous functions. And so we can similarly consider other sorts of nice types of functions. For example, we can talk about differentiable functions. The notation for this is C1 of RR. That 1 indicates that you can take the derivative at least once. And you could also define C2, C3 as like spaces of functions where you can take the derivative twice or 3 times. But sometimes it's nice to just go all the way to C infinity, which is what are called the smooth functions. These are the functions where you can take the derivative any number of times and you never run into a problem of them not being differentiable anymore. Most of your favorite functions are in this space. For example, e to the x, you take its derivative, you just get e to the x again, and you can keep taking its second, third, fourth derivatives and keep going forever, and you'll never run into any problems. So e to the x is in C infinity, sine of x, cosine of x, and polynomials. Eventually with polynomials, you keep taking the derivative and you'll get to 0, but that's totally fine. And then actually, because they're so nice, you could just consider polynomials. And the space of polynomials has this special notation. It's just P. So all of these examples are subspaces of f of RR, and therefore they are vector spaces in their own right. So a particularly important example for us is going to be this space Pn, which is the space of polynomials of degree less than or equal to n. So for example, the elements of P2 are of the form a plus bt plus ct squared, where a, b, and c can be any real numbers. And we can describe elements of Pn in a similar way, like this. So these examples will come up quite a bit later on, but for now all you really need to know is that when you see P2, P3, or whatever, this is what it means. So a frequently asked question is, what's the difference between a vector space and a subspace? And the answer is that subspace is a relational term. Whenever you talk about something being a subspace, that means that there's some other vector space lying around. And what you really mean is that it's a subspace of that other vector space. And sometimes it's clear from the context what that other vector space is, and so you don't need to say it, but that's always implied when you're talking about something being a subspace. And then on the other hand, when you say that something is a vector space, that's something that's an intrinsic property of that thing itself, and it doesn't require the existence of anything else. And so when I say that a subspace is a vector space, what I mean is that if you can recognize something as being a subspace of another vector space, you can forget that that other vector space exists, and you can just treat the subspace as a vector space in and of itself. A good analogy for this is, okay, I have a son. When I say that he is a son, that's a relational word. He can't be a son without having parents. So that's sort of like saying that he's a subspace. But being a son means that he is also a person. And when we talk about him being a person, then the parents don't play any role in the story anymore. He gets to be a person who exists independently of anybody else. And so saying that my son is also a person is analogous to saying that a subspace is also a vector space.